So today we're continuing on with reinforcement learning. And this lecture, there's no great way that I've found to structure it. It's a little bit disjointed. So we're going to introduce 2 or 3 little topics and then try and tie them in together by the end. So I promise it should make sense by the end of the lecture. So there's just a couple of things, so like discounting, continuing tasks, etc. And then there's a formula and a concept by the end of the lecture where hopefully things start to make sense together. First, we're going to introduce this concept called discounting. And what discounting does is that the agent tries to select actions so that the sum of discounted rewards is maximized. So we've been saying so far that we want to maximize this return. So the return here is g of t. And so far in the class, we've been talking about the next reward plus the next reward plus the next reward, etc., up until like the end of this episode. Well, it turns out that in some cases, what we're going to want to be able to do is value rewards differently based on when they happen. And so a generalized way of doing that is this concept called discounting. So discounting, typically we pick this value of gamma as between 0 and 1, and that's called the discounting rate. And so the discounting rate, here's the formula. And so the sum from k equal to 0 to infinity of gamma to the power of k. So gamma to the power of k when k is 0, anything to the power of 0 is 1. So what we get is g of t, which is the return, is equal to, okay, the full first reward, the next reward that I'm going to get, plus gamma times the next reward, plus gamma squared times the next reward, etc. So if we think of this in terms of, let's do an example of gamma equal to half, for example, then our return would be equal to the next reward plus half of the reward after that, plus a quarter of the reward after that, plus an eighth of the reward after that, etc. So by setting gamma equal to 1, we get the formula that we've been using so far, right? Because 1 to the power of anything is just 1. So if this was 1, then we'd get the next reward plus the next one plus the next one plus the next one. If it was 0, then all we would do is care about this reward, right? The next reward, because 0 to the power of anything except 0 is going to be 0, and so it will be just the next reward. So if gamma is 0, we only care about the next reward. As gamma goes to 1, we care about all future rewards equally. And if gamma is somewhere in between, then by multiplying gamma by itself, we get less and less trust in future rewards as time goes on. So this is not, we have not applied this to anything yet, but it is part of an eventual equation. And rather than show you the equation first and then explain what gamma is, I want to show you this concept first. So the discount rate determines the present value of future rewards. So a reward that you get k time steps in the future is only worth gamma times to the power of k minus 1 as much as if it was an immediate reward. And if gamma is 0, the agent only cares about the next reward. If gamma is 1, then the reward formula is the same as the episodic formula that we've been looking at so far. And so as gamma approaches 1, the agent becomes more farsighted and cares about those rewards. So if we look at returns, returns at successive time steps are related in a mathematically important way. So this would be the return at time step t that we've been looking at so far. And that is the next reward plus gamma times the next reward plus gamma squared times the next reward, etc. But if we look here, this term is actually g of t plus 1. So if g of t is rt plus 1, ... then g of t plus 1 is r of t plus 2, ... And so the return that I get at a particular state is equal to gamma times the return I would get at the next state plus the return that I just got. And so what this means is that the return I get at a particular state is related in some mathematical way to the return that I would get at the next state plus my reward. So this idea that the return I would get at state S is somehow related to the return that I would get at state S sub prime is going to be very important a bit later in the lecture. So that's one concept, is this concept of discounting and how returns are related to each other based on the states. Now, I'm going to introduce another concept, which is continuing tasks. So we talked about episodic tasks. Episodic tasks are when we have a sequence of actions and then there's a terminating state. And so these episodes are considered independent. For example, a play of a game. So if we're playing blackjack or poker, we may have an episode being one hand of that game of cards, right? So the dealer is going to deal some stuff out, we'll have some bets, and at the end someone will win or lose, and then the episode will go away, and then we have another episode. Or we could think about a pathfinding example where we have one trip through a maze, I get to the goal, or maybe some time limit is reached, and then I respawn in another place, and that's another episode. And so the return for those episodes, without the gamma we just talked about, is g of t, which is just the sum of the future rewards up until this time step t, which is the end of that episode. And again, the end of the episode could be terminated by some goal condition being reached, or maybe we have like just a set number. If I don't reach the goal in 100 time steps, that's the end of the episode. So the object of the agent is to determine a policy which maximizes the expected return of that. However, what if the task doesn't break easily into episodes, right? Like real life, right? We don't have really episodes. I mean, maybe you could consider one day, one episode, just trying to get from one day to the next, but really, life is just one continuing task. So continuing tasks are tasks that go on continuously without a limit. So for example, think if you have a long lifespan robot where it's just continuing to do something over time, or a control task. So maybe there's a robot on an assembly line, for example, right? And it keeps getting better over time. Or I've made a robot that constantly watches guard somewhere and never actually has an episode where it like goes to sleep and then comes back the next day or something like that. So there are lots of things that we can consider as continuing tasks. And so the reward that we've been looking at so far, the return that we've been looking so far, this formula stops somewhere. And the final time step is at t, but for a continuing task, t is probably going to be infinity. So how do we do this, right? How do we take this concept of a return, which is this finite sum, and then do this for continuing tasks? So what we're going to do is introduce this unified mathematical notation, where we're going to have the same notation for both episodic and continuing tasks. And it will turn out we're going to modify our definition so that an episodic task is actually a special case of a continuing task. So everything is a continuing task, except what we're going to do is we're going to add a final, what we call absorbing state that just loops forever. Okay, so if we want an episodic task, for example down here, if our task has 3 time steps in it, but we want to represent that using an infinite sum, like we were just looking at with discounting, then, okay, well, k equals 0 to infinity, that doesn't really work for an episodic task where we have a finite t. So what we do in order to make this formula work for finite t's is we just pretend, okay, at some point I reach a state where we just loop forever and get 0 reward. Okay, so it's kind of a cheesy way of turning an episodic task into a continuing task, but it lets us apply this theory to all of our types of tasks without having to have one for finite tasks and one for infinite tasks. Okay, so this is this idea of a unified mathematical notation. That's like idea number 2. Now let's look back at the last lecture, just as a recall, where we talked about action values at a state. So Q of A is the value of an action. We did a big example with the slot machines and the table. So Q of A at its time step t was our value of doing, or our guess or belief at the value of doing a particular action. And the value of a specific action will vary at the state it was issued, right? So for example, in the example we did, there were just 4 slot machines, but at the end I said, if you're actually doing a task, like a real-world task or something like pathfinding, then essentially what you have is at each state of the environment, you have 4 slot machines. So for example, moving up is good if the goal is up, but if you're already above the goal, then you don't want to move up. That has a lesser value than moving down, for example. So what we introduced was the idea of a value of an action at a state. So rather than just Q of A, where there's the value of going up, really what we have to keep track of is the value of going up at a particular state. So the value of doing an action at a state. And so if we had these n different actions, for example, if I'm doing this pathfinding task, right, I essentially have this analogy of a slot machine at every different state. And then I would have estimates of my values at each state. So at this state, I have an estimate of a value for going up, I have an estimate of a value for going right, estimate of a value for going down, etc. But if I was at a different state in the environment, these values may be different, right? The value of going up or left somewhere is different from going up or left here. Okay, so now, based on that, we're looking at the action value function Q of pi. What is Q of pi instead of Q of A? So Q of A what's the value of doing that action? Q of pi is the overall value if we keep doing actions from a policy. So remember what a policy was, it was a mapping from states to actions. So it'll tell us exactly what actions to do at each states. So instead of just Q S of A, it's Q pi of S of A. And this basically tells us what is the expected return if we start from state S, do action A, and then keep following a policy pi. Okay, so I've done one action, but then I'm going to do actions from my policy after this. So Q pi of SA, mathematically speaking, is the expected value, right? The expected value given a policy. So I'm going to keep doing the things in a policy. And so for example, before I get into that, let's say you have a policy of always going up, right? That's going to have a different value given a state if you have a policy of always going down. Or always betting in a game of poker versus always folding, right? The policy is going to give you different values. So Q pi of SA is the expected value given a policy of this return, G of t, given that the current state is S and the current action is A. So I'm at a given state, I've chosen a given action, and then I'm going to follow policy pi from that. And so this return formula, as we just saw, is the expected value of the sum of future discounted rewards, given that we have taken an action at a given state. Okay, so now it's starting to come together a little bit. We're unifying everything just a little bit more. Now we can think of a state value function, which is what is the value of being at a given state. So V pi of S is the expected return starting from state S, and then instead of following an action first and then following a policy, we're just going to follow a policy from state S. So I think this one kind of makes intuitive sense, where you're at a given state, you follow a policy, and then whatever is the sum of future discounted rewards that you get from following that policy from that state, that is the value of a state. Okay? So the value of state S given a policy pi, very similar to the last one, except we're not taking an action first. So it's the expected value of the return given that you're at state S, which is just the expected value of the sum of discounted rewards starting at state S and following policy pi. So I've given you a policy to follow. Maybe it's a blackjack betting chart, right? So for example, in blackjack, the optimal policy, if you look at an optimal policy and you play against a casino, you're going to lose about 52% of the time. That's just the way it goes. So if you play optimally and you're making $1 bets, you're going to lose on average 52 cents per bet, right? So if I asked you what is the value of the starting state of blackjack given the optimal policy of blackjack it would be slightly negative because you'd be winning 48% of the time, losing 52% of the time. Okay, that's another concept. One more. I know I'm overloading you with concepts here, but hopefully they're not too difficult. This one is called the Markov property. And so we've already talked about this before, but I didn't give it a name. So in a reinforcement learning framework, an agent makes decisions as a function of the state of the environment, right? Pi is our policy based on a given state. So the state of an environment, again, is everything that's available to an agent. And if a state contains all the relevant information for making a decision, then it is said to be Markov or to have the Markov property. And so intuitively, if we look back, this was like lecture number 2. If we don't need any state history of moves, then it is said to have the Markov property. So for example, in a game of checkers or a game of chess, if 2 people have been playing a game of checkers or chess inside a room for a half an hour, and you just walk in and you look at the board, you could tell them the optimal move, right? You don't need to know what has happened already in order to help them make the optimal move for a game of chess. So we've looked at that example, but we looked at another example for League of Legends, right? Where you have Team Liquid Piglet up here stealing a Baron kill, but he didn't know what the life of the Baron was, right? But because earlier on, like maybe a minute before, he had seen the people walk into the Baron pit, he knew, okay, a minute ago they had walked in, they can probably do this amount of damage, so I'm going to make an educated guess at that. So that from the point of view of Piglet, you needed to have the full history of the game, or at least the last minute, in order to make a decision like that, right? So that would not be considered Markov because you did need things in the past. Now, what you can do to take a non-Markov thing and make it Markov is do this kind of cheesy hack where as part of the state, you encode the state history. But, in a purist way, this is not a Markov decision-making process here. So, the definition of the Markov property, in general, for every possible problem, environment, state, and rewards may be dependent on the complete action sequence. So for that League of Legends example, it was dependent on the complete action sequence. And what that means is the probability of the next state being a particular state and the next reward being a particular reward is dependent on, this means depends on, or is based on, the entire state history so far. But if the Markov property holds, then at t plus 1, that only depends on the state and action at time t. So the Markov property holding means that the probability that a current state is S prime and a current reward is R is only based on the current state and the current action, which would be more like a game like chess or checkers. So that is the definition of the Markov property, and if that holds, then the environment or the problem or the game is said to be Markov. So now, and Markov is just someone's name who figured this out a long time ago. So a Markov decision process, or MDP, has anyone heard of an MDP before? A couple of people? If you're in engineering, you've probably heard of it. But any reinforcement learning task that satisfies the Markov property is called a Markov decision process. So if you ever hear MDP or Markov decision process, now you know that you know what it is. And if the state and action spaces are finite, it is called a finite MDP. And usually in an academic setting, especially in an undergraduate course, we're going to be talking about finite MDPs. And so here is the definition of a finite MDP, which is kind of the definition of a reinforcement learning problem. So in one way, you can look at an MDP as being a way of phrasing a problem that can also be solved by reinforcement learning. So here we have an MDP, which is S, A, P, R, and gamma. To myself, whenever I have to remember this for an exam, I just think of SAPRI. And so this is not a Y, it's actually a gamma, but it sounds a lot better than SAPRG. So I just say SAPRI in my head. And if I'm saying this, it may be part of an exam. Wink, wink. So S here is the finite set of states. And so that is the states that we have in our environment. A is the finite set of actions. And so A sub S are the actions that are legal from state S. P of A, S, S prime, that is the probability that the next state is equal to a given state, given that the current state is a particular state and the next action is a given state. So what do I mean, the probability that an action takes us from one state to the next state? Well, in a game like chess or checkers where there's no randomness, then a particular action will always take us to a particular next state, right? If I move my pawn, if I say issue the action of moving my pawn up by 1, it will always take me to that action. However, if I'm in a game like blackjack and I say hit me, that may lead me to a state where I've won the game, or it may lead me to a state where I've lost the game. Because the actions of dealing cards, or if you have a game like dice or backgammon, anything with randomness in it, this is essentially giving, these are the details of that probability, right? So what are the probability that rolling a dice will take me to jail in Monopoly, right? That's what this is doing. And like I said, if your game is deterministic, then this will always be 1 for those actions. Down here we have the rewards. So the rewards are RA, S, S prime. And what this defines is the reward after transitioning from state S to S prime using a particular action A. Okay? So it may be, the reason it's phrased like this, the reward after transition from S to S prime via A, is that you may be able to get from one state to another state via 2 different actions, right? So for example, if I'm in blackjack and I've chosen to hit versus stick, 2 different actions, both of them might take me to the eventual winning state where I both win $100, right? Or if I'm at the same state and I've chosen the same action, it may lead me to 2 different states. Like hitting may lead me to winning or losing, right? So here we have to be very specific that the reward technically only comes from being at state S, then taking an action, and I've gotten to a specific state. Okay, so that's what the reward is. And then we have gamma down here, which is the discounting factor. And so the point of an MDP is that we want to find a policy somehow that maximizes this value. Okay, so it maximizes the sum of future discounted rewards. And if I had just shown you this at the beginning, then there would be a lot of questions, like, what the hell is gamma? What if we have an episodic task, right? So I wanted to just introduce all those things at the beginning, so now we know what that means, right? We have some task, whether it's episodic or it's continuing. We have a discounting factor. We have rewards that are being given from actions, and this is the value that we want to figure out. Now, the thing that I'm going to be introducing in this lecture is one way of possibly figuring that out, and that's called dynamic programming. So have any of you done dynamic programming so far? Maybe most of you at a third year, half of you. So it's a pretty standard thing. And what dynamic programming is essentially if you have one subproblem solved in a given problem, you can determine the answer to another subproblem by using the answers from other problems. Okay? So if you think about it in terms of like a matrix, if you've got some answers filled out in a matrix, then you might be able to, for example, fill in the values of the neighbors from that matrix. It's a very hand-wavy view of dynamic programming, but what we're going to be doing is an example of tabular dynamic programming. And once I get into the actual visual examples, this should make a lot more sense. So what is dynamic programming? It's a collection of algorithms that can compute optimal policies given a perfect model of the environment. So what we'll see is that dynamic programming is very powerful. It's relatively inexpensive. It's very, very fast to perform. However, the downside of dynamic programming is that you need a perfect model of the environment in order to do dynamic programming. And if we analyze it even further, it turns out that even if you have a perfect model of the environment, you also need to know the state transition probabilities in order to implement dynamic programming properly. So while theoretically it's great, It's not going to be something that we really ever get to use in practice. However, its theoretical properties will lead us into better algorithms in the next couple of lectures when we talk about temporal difference learning, stuff like that. So the main idea that we are going to look at with dynamic programming is that the value of my current state is somehow related to the value of my neighboring states. And so we're going to be using dynamic programming to compute the value function. And then, once we have the value function, we're going to use that to compute the policy. So let's look at an example. And let's go to old, trustworthy grid world pathfinding example. So I am at a particular state, x, y. I've got these actions. I don't need to explain what this is at this point. But I've got these particular actions, action 0, action 1, action 2, and action 3. Now let's say that somehow I have been given the values of my neighboring states. Okay? So the value of going up, so that state's value is 20, this state's value is 0, that state's value is 10, and this state's value is 30. Okay? So I've been given those values. And if you think about it, if those are the values of those states, and the only place I can go from this state is one of those states, then my value at this state is probably related to those states, right? So let's look at how that is. But you may say, okay, but don't we need to know where we're going? So for example, if I told you that my policy at state S was to always go left, then the value of this state would be equal to the value of this state. So if I'm somewhere that I don't know the value of, but the only place I can ever go has a value of 30, then the value of where I am is also 30, right? The value of being in a car going 100 kilometers an hour 1 meter from a wall is the same as half a meter from the wall, is the same as hitting the wall, right? The value of being that state, if it's inevitable where you're going to go, is the value of the eventual thing, right? So what we have to do is talk about action probabilities. And the action probabilities are given by our policy. It tells me with what probability I want to take each action. So if I have these values at this state, let's just say, for example, my policy doesn't really know much yet, and so it says, just take them equiprobable, meaning with 1/4 probability I'll go up, 1/4 probability I'll go down, or left, or right. So if I'm going to go with 1/4 probability for each of them, then the formula for computing the value of the state that I'm at is 1/4 times the value of each state, and then sum that up, right? So I have 1/4 chance of getting 20, 1/4 chance of getting 10, 1/4 chance of getting 0, and 1/4 chance of getting 30. So can anyone do that in their head? I've made the numbers kind of easy. Add the numerators together. 15, okay. It wasn't a trick question. So it's just 30 plus 20 plus 10 plus 0, 60 over 4, which is 15, right? That's a good exam question. Not this exact question, but like, that's a good exam question. Now you may look back at the sum of future discounted rewards and say, what about gamma? Right? Well, gamma is just 1 for this example. Okay, we haven't factored in gamma because it makes the numbers. If I say gamma is 0.9, who wants to do a bunch of 0.9s, right? Okay. So the value of this state then, given an equiprobable policy, is 15. And this is the essence of as far as I want to go with dynamic programming in this course, but it's just saying if I know the values of neighboring states, then I know the value of the state that I'm at if I'm given a policy. Here's another example. Let's say you're this guy. You probably don't want to do this. Maybe it's exciting, maybe it's not. But this is my current state. Not my current state, because I'd definitely be going over the cliff. But let's say you're in this state. Let's say you're really good at this. So you have a 90% chance of the next state, a couple of seconds from now, being you not next to the cliff, right? You're safe. So maybe that you get a reward of 10. Ooh, that was a rush, right? You get a little rush from that. Okay, so it's 90% chance that I'm safe, but like a 10% chance of a really negative reward, right? So you want to ask, what is the value of the current state? Well, if I've given you the probability, so I've given you the policy, well, the policy doesn't say with 10% chance, go off the cliff. But the policy states, hey, get away from the cliff. And then that P of A, S, S prime, that probability of transitioning, you're not perfect, right? So the probability of taking the action of be safe, get away from the cliff, actually resulting in these states, that factors in these non-deterministic situations. Now, in real life, there is a skill level involved, and so you're not rolling dice, but who here has never tripped, right? You don't mean to trip. Like, I've tried to tell people, hey, that looks kind of unsafe. They're like, yeah, I'm not going to fall. Nobody plans to fall, right? And then this guy ends up on some website where they post bad videos, right? So if I want to compute the value of the state, I would take the probability of each of those states occurring, multiply their values by the probability, and sum it up. So if you are a unicyclist with the skill of only 90% chance of being safe, you probably shouldn't do this, right? Now, that doesn't mean that, oh, let's find the value of skill for that going next to cliffs is actually worth it, right? Like, let's not go that far. But this is just another example. And the point here is that the state value depends on the policy. Why is this a scary picture if it happens in real life? Why does the parent get up and run toward the baby in this state, but doesn't get up and run toward you in this state? Sure, but more realistically, like, if you're old and still at a baby level of stove intuition, right? So the point here being that the adult knows that the baby's policy has not gone through enough iterations to know what to do here, right? And not only that, but even if the baby knows what it should be doing, grabbing the handle and moving it, the probability of reaching its desired state is probably pretty low because of its motor function abilities, right? So it's dependent on the policy. This is a scary state for this person, but not for an adult person, or most adult people. Okay, so that's like an important thing. All right, here's another example. This is from assignment 5. And what I've done in assignment 5 is I've essentially colored the spaces, and again, so assignment 5, which isn't out yet, this is a grid world pathfinding example that I'm sure you all are excited to get another one of these. But you are this blue agent here. You're going to be put in a random part here of the environment, and you have to form a policy which says, get me to the closest terminal state. Once you get to the closest terminal state, it'll teleport you to another random state, and then you'll try and go back. So what I do here is I've colored the squares based on the value of a state. And if it's red, it's negative. So essentially, the more red a state is here, the further away it is from the goal, right? Because we're going to say, hey, if it's a non-terminal state that we're at, then every action is going to give you a -1. Therefore, solving that MDP is going to maximize your sum of discounted future rewards, which means that you're going to minimize the negative. So it'll minimize the path distance to the goal. But the point of this lecture, or part of this lecture, is to talk about dynamic programming. And so, for example, if I had told you, if I had hidden this particular square from you, this one right here, and then asked you, what color would that square probably be? Right? Even without knowing what dynamic programming is, you could probably tell me that, hey, this is going to be a value of red that's probably between that one and that one. Right? Even without knowing anything about value functions or dynamic programming or the mathematics behind it all, there is an intuition in you somewhere that says the value of states is somehow related to the value of neighboring states. And dynamic programming and this update function that we've been looking at are just a mathematical way of expressing that intuition. Similarly here, this is from another grid world example where instead of we've got the values here labeled with numbers instead of just with colors. This is not from my assignment, but it was a cool thing I found on Google Images. So again, the numbers here are related to their neighboring states, right? So if I'm right here, if I didn't know that this was a 6, but I saw going up gives me 7, going left gives me 7, but going right or going down gives me 5, I could probably somehow intuit that the value of this state was 6, right? So tying this all together now, we have the Bellman equation. Has anyone seen the Bellman equation before? Oh, we got someone. What class?
Reinforcement learning.
Oh, well, there you go. Which class was that?
I was in the math department.
Oh, math department. Cool. So all this, you don't need to know any of this stuff, then you already know it. So policy evaluation and value evaluation. So let's compute the state value function, v pi, for an arbitrary policy pi. And we use what's called the Bellman equation. And this is a very scary looking formula. I understand that. I hate math formulas. What I like is code. And so we're going to try and talk about this in terms of code. And wherever you see a summation, that's basically a for loop, right? So it makes it a little bit less scary. So what does this mean? It means that the value of a state given a policy pi is equal to. Now, the first thing here is just saying that we're going to look over every action at a given state and see the probability of doing that action. So that is the policy pi here. So for example, if your policy said, hey, with equal probability, move up, down, left, and right, then this term for each action would be 0.25. If it said, hey, for the action of moving right, do that 100% of the time and never go in any other direction, then for the action of going right, this would be 1, and it would be 0 for every other action. So this is the outer for loop here that says for every action that's legal at a state, get me the probability of doing that action. That's what my policy tells me to do. In here, the inner for loop says, what is the probability that given I'm doing that action at this state, that I go to the next state? And if we are working in a deterministic environment, this value right here is always 1. So most of the time, we can just remove this right here, right? But that is not true for a game like blackjack or other games that have randomness in it. And then inside here, this is just the reward that we got from doing action A at state S, which gets me to state S prime, plus gamma times the value of the next state. It's literally what we've been looking at the whole time. It's just all summed up in one equation. Okay? So let's break that down a little bit more. So this is the same equation, but what I said before is that in the case of actions deterministically transitioning one state to another, this is always going to be 1. So if it's always going to be 1, then we can just remove it, and what we've got left is this here, which is the exact example that we did of moving up, down, left, and right, multiplying them all by a quarter, right? So for that example, one of these, we had a value of the next state being 30. One of them was 20. One of them was 10. One of them was 0. The only thing that's different is we also have a reward from doing something at this state. So in that example, we did not have a reward, but if we did, we would just add that each time, okay? So on an exam, I could say, here's a little matrix, here's an up, down, left, and right, here's the values of those states, here's a value for gamma, and here's the reward that you're going to get, compute the value of this state based on that. And so that is using the Bellman equation. You have a question?
If the value of the next state is not already stored in the dynamic program memory, then there will be recursions, right?
Yes, but I'm not going to go that far in this course. I'm just going to say, here's one state, do this, right? So like if we have the value of one state next to one and we don't know that value yet, then okay, well, we need to know that value, so maybe you apply the Bellman equation to that one, but that one needs to know this one. And so how do we determine that? Well, it's a multi-stage process, and it can be done, but we're not really doing dynamic programming in this course because I don't think it's super interesting. It's just applying a formula. But I want you to know where this Bellman equation comes from. So the fact that dynamic programming tells you that the value of states are related to the value of future states, that is going to be a part of the eventual formula for temporal difference learning, which we are going to learn in another lecture, which is going to be what we are using for assignment 5. So in assignment 5, or in a future lecture, we're going to be talking about something like Q-learning or SARSA, which are really easy formulas. But what they do is they use part sampling and part the value of the next state. And so we combine them into one formula, which is called temporal difference learning. So this up here, this is just the formula that I had in the last slide, which is probably occluded by my face, but that's okay. And we're going to put this into code now so that we can all fully understand it. So v pi of s, we need somewhere to store that. So that's just v of s. Then the policy that we look up, p or pi, actually in its native Greek, pi is actually pronounced p. So it's good that we use the p down here. So p of SA, that is something we can look up. So it's the probability of doing action A at state S. Then, if we wanted to do this for each state of the environment, we could have a for loop that says for each state. So we're going to set initially Vs equal to 0. Then, for each legal action A at S, which is what this loop is for looping over summing for each action A, we look up PR, which is the probability of choosing A at S, which is just equal to P of SA. And in assignment 5, we'll have a P of SA, which is looking up our policy. Then we get the reward from doing action A at state S. Then we get the next state, which is just applying action A to state S. Then what we do is we say Vs, which is currently 0, we are going to add the probability, the probability of choosing that action times the reward plus gamma times V of S prime. And this for loop here is exactly what we are doing right here. So that is just the mathematical formula in terms of actual code, which I personally find much easier to understand. So now we've got the value. But values don't matter unless we know what to do, right? The whole point of solving a reinforcement learning task is to form the policy. So how do we do our policy update? Well, we just take the action at S, which leads to the highest value. That's it, right? So whenever we're at a state, policy update is really simple. So we just computed that. If we want to know the value of doing an action A at state S, look it up in the resulting V of S prime, right? So you take the action, look at where it gets you, and then that's the value of that action. So to update the policy, you just choose the action which has the highest value. That's it. Or leads to the state with the highest value. And so, if we actually want to update our policy PSA in code, here is the code to do that, and you can copy and paste this for assignment 5 and turn it into JavaScript. So, P of SA, this is really small. I apologize for that, but you'll be able to see it on the slides. So P of SA is what we're trying to determine. That is the probability of choosing action A at state S. And we've got two variables here. One is called max A. That is going to be an array. And max A, let's say we've got a bunch of, let's say up and down, both have the same maximum value. Then max A is going to store up and down. So max A, eventually, once we've done the algorithm, is going to store all of the actions that produce the maximum value. Then we've got max V, which is the maximum value of any state leading from this state. So initially, if we're maximizing, this is going to be negative infinity. So for each legal action, A, at state S, we're going to get the next state, which is applying action A to state S. Then, what are we going to do? Well, based on the action and the value, so the value is going to be V of S prime, right? That's the value that we get from doing action A at state S. So there's two possibilities here. One is I don't have any maximums yet, and the other probability is that I have some maximums already. So in the case where I don't have any maximums yet, well, that's pretty easy. I just add this action to the maximum actions, and the current maximum is equal to the value of this state, right? So if this is the first action that I'm looking at, it's obviously the maximum so far. But that's not really the interesting one. So we say else. So this means that there is at least one maximum action so far. So if There's three cases now. If there are maximum actions already, either the current one is greater than that one, it's the same as that one, or it's less than that one. And so we're just going to have different cases. So if the value of taking the current action, so the value of the next state, is equal to the maximum value, then it's another maximum. So all I have to do is add this to the maximum actions. So let's say I just looked up, and the value of the state at looking up is 5. Now I'm looking down, and the value is also 5. Then this triggers, and I just add down as well. So now I've got up and down. The next case is where I have a new maximum. So the value of this one is bigger than anything that I've done so far. In that case, I want to clear out my maximum actions, right, because I have a new maximum. Then I am going to insert this new maximum. So I have an array containing just this maximum, and I have a new maximum, so I have to set the max value. And the last case is where I have a value that is less than the current maximum, in which case I don't need to update anything. If it's not a new maximum or equal to the current maximum, then I don't need to do anything, it's just worse. Okay, so now what I have is I have the value of the maximum, and I have all of the actions that produce the maximum. So I have to update the policy to point toward all of the things that give me the maximum. So for each legal action A at S, if A is in the maximums, then the probability that I should do A is 1 divided by the number of maximums, right? So if there are two maximums, if up and down both give me the maximum value, then I should go up with equal probability of going down. So both of those would get 1 divided by 2, which is 0.5. And I put in the 1.0 here just to make sure that this is not integer division, it's floating point division. And then if A is not in max A, then the probability of taking that action is 0. If the action does not lead me to the most desirable state, why would I take it? Right? And of course, at some point at the beginning, in order to start doing actions to get values, maybe your initial values for all of the PSAs are going to be randomized, for example. So at the very beginning, we don't know what to do, so take actions with random probability, but then as we find values, we update them here. So what this says is look at the values of all the neighboring states and update the policy to have an equiprobable chance of selecting all actions with the max value, or if it's not a maximum value, it's 0. So let's just do a quick example, because examples are always how I learn. So let's say we have 5 possible actions, A1 through A5 at a given state S. They are going to yield 5 new states, state 1 through state 5, and those state values are going to be 10, 0, 10, 5, and 10. And so the actions which yielded the maximum values, once we've run that algorithm, we get this array. So this would be the max A array. So action 1, action 3, and action 5 produced those maximum values. Therefore, the new policy should be equiprobable in choosing A1, A3, and A5, and 0 otherwise. And so we take 1 divided by the length of max A as the value for the probability of choosing P1, P3, or P5, and 0 otherwise. So that's pretty simple. And this example, if I give you these values and say on an exam, show me what the policy should look like afterwards, that should be pretty easy, right? Just take the maximums and divide 1 by the number of maximums for each of those. So what we will look at is that we've got some values, then we update our policy, and then the point of reinforcement learning, or one of the ways we do reinforcement learning, is to then take that updated policy, use it, then update the values, right? And then we look at the values, we update our policy, we use the policy to update the values, and this is an endless cycle. So obtaining an optimal policy involves these 2 steps repeated many, many, many times. So we update the values based on actions taken from the policy, and then we update the policy to choose the actions which lead us to the maximum valued states. And this goes way back to way back to last week where I first showed you this slide, but where I had the agent is going to take some actions, but what I had not included on that slide yet was that those actions are taken based on some policy. right? So the agent takes some actions based on a policy, we get a reward, we go to the next state, and then in here, we update the value of the actions at those states, and based on the state and the reward, and then we update the policy, the agent has a new policy, and this cycle repeats and repeats and repeats and repeats and repeats. So some possible exam questions based on this, action value and state value, so what is Q of SA versus what is V of S. The properties on MDPs, I could give you, for example, the description of a problem and ask you if that fulfills the Markov property, so is this an MDP or is it non-Markov? I could ask you to give me the properties of an MDP, so the SAPRI thing, S, A, P, R, and gamma, what do each of those mean? I could give you an example of dynamic programming and ask you to compute the value of an intermediate node. I promise you I will make it so that the values work out to be integers, so you won't be doing weird floating point calculations. So given neighboring values, calculate V of S using the Bellman equation. A policy update, so given some values, update the policy. That could even be a two-part question where I give you neighboring values, then have you update the current value, and based on that, then we do a policy update. Or I could ask you to state the Bellman equation, or write, no, I won't get you to write the pseudocode of the Bellman equation, but you could be asked for the Bellman equation, for example. And that's it. This is a particularly short lecture, but it was kind of dense, and if you don't understand it all right now, I am not surprised. There could be some exam questions on this, but I promise you all of this is leading somewhere, and it will be the algorithms that we end up using on assignment 5.